In this video, we will be discussing colligative properties and looking at how they change with changing concentrations. Colligative properties are those that depend only on the concentration of the solution, not the identity of the solute. We will be looking at four different colligative properties. The first is vapor pressure. The second, boiling point elevation. The third, freezing point depression. And the last, osmotic pressure. When two volatile compounds are mixed, some of each will evaporate. In this evaporation process, some of each one of the liquids will go into the gas phase. How their gas phase concentration, which will be measured as partial pressure, compares to what they would be if they were pure, depends on their concentration in the solution. This applies to both the solvent and the solute. Mathematically, this follows what's called Raoult's law, in which the partial pressure of a given component is equal to the mole fraction of that component multiplied by its vapor pressure when it is pure. We can look at this graphically for an ideal solution, defined as those that fits perfectly with Raoult's law. Along the x-axis, what we are looking at is the mole fraction of component A. On the far left, we have a 0 mole fraction, meaning that the solution is purely the B component. And on the far right of the r-axis is a mole fraction of 1, meaning that the solution is purely A. In the middle, we have some mix of component A and component B. Starting on the left-hand side, the vapor pressure of the solution is going to be equal to the vapor pressure of component B because as we start, we don't have any A in there. If we increase the mole fraction of A, then what we find is that the amount of A that is in the gas phase increases as we increase the mole fraction until we get to a point where the solution is purely in the A form, at which point the vapor pressure is the same as A because the solution is at this point purely A. In the middle, as B decreases in concentration, the amount of B in the gas phase is lower than what it would be if it was pure. When we add the two partial pressures together, we get the total vapor pressure of the solution. Now, solutions do not always follow perfectly with Raoult's law. We can have two cases in which the solute-solvent interaction are either positive or negative, meaning that they are strongly attracted to each other or they are not strongly attracted to each other. In the case where we have strong solute-solvent interaction, what we find is that the actual amount of vapor that goes into the gas phase is less than what we would expect. And this is because the solute and the solvent are interacting to keep both in the solution phase. In the case where we have a weak solute-solvent interaction, we get a positive deviation from Raoult's law, in which the total vapor pressure of the solution is higher than what would be predicted by Raoult's law. The reason for this is because there is weak intermolecular interactions between the solute and the solvent, more of each will be present in the gas phase. Let's now look at a problem using vapor pressure. We will determine the vapor pressure of a solution at 25 degrees Celsius that contains 76.6 grams of glucose, chemical formula C6H12O6, in 250.0 milliliters of water. The vapor pressure of pure water at 25 degrees Celsius is 23.8 torr. First thing we'd want to do is write out our equation so we get an idea of what we're looking for. So Raoult's law for vapor pressure is the pressure of the component, in this case we're interested in water, is equal to the mole fraction of our component, in this case water, times our vapor pressure at that particular temperature. Because we're looking at 25 degrees Celsius, this is a standard state. So we'll look at P naught for H2O. This pressure here is the vapor pressure when the solution is pure. Mole fraction, as a reminder, of a particular component is equal to the number of moles of that component divided by the total number of moles in the solution. So what we will need to do is find those two numbers. We need the total number of moles for water, and we will add to that the total number of moles of glucose. So to get the number of moles for glucose, C6H12O6, that is equal to our mass, 76.6 grams, multiplied by our molecular weight. 1 mole of glucose weighs 180.15768 grams. Grams cancel out. This will give us moles of glucose. Plug this into your calculator, you will get 0.42583 moles of C6H12O6. In terms of significant figures, our first value has 3, our second value has a lot more than 3, and so that is where we will cut and round our value. Next, determining the number of moles of water that we are working with, we'll take 250.0 milliliters. The density of water at 25 degrees Celsius is very close to 1 gram per mil. So we'll multiply this by 1.00 gram per 1 milliliter. Our milliliters cancel out. Take this, multiply it by the molecular weight of water with the mass on the bottom. 1 mole over 18.01528 grams. Our grams cancel out, giving us moles of water. This is 13.877109 moles of water. Our value for our density had the least number of significant figures, so that is where our sig figs will end. The mole fraction is just the ratio of the component that we're interested in, which in this case is water. So this would be equal to the moles of water, 13.877109, sig fig marked there, divided by the sum of all of our moles. So that would be 13.877109 for our water plus our glucose, 0.425183. Sig fig marked there, sig fig marked there. When you plug this into your calculator, you'll get 0.9702717 sig figs. We'll have 3. To find our vapor pressure of water, we take our value 0.9702717 sig fig mark there, multiply that by our vapor pressure of the pure water at that same temperature, which is 23.8 torr. If you plug this into your calculator, you will get 23.09247 torr. In terms of significant figures, we will have 3 for our answer. So our end answer would be 23.1 torr. If we wanted it to be in a different pressure unit, we could then apply the necessary conversion factor at this point. The next 2 colligative properties that we will be looking at are the freezing point depression and boiling point elevation, both of which represent a temperature change for the phase transition between the liquid phase and either the solid phase or the gas phase. The presence of a solute in a solvent stabilizes the liquid phase, making it more difficult to solidify, also known as freeze, and vaporize, also known as boil. The freezing point depression can be defined as the reduction in temperature needed to cause the solvent to freeze. The boiling point elevation is the increase in temperature needed to vaporize the solvent. Again, because we're talking about colligative properties, the only thing that matters is the concentration of the solute in the solution, not the identity of the solute. That said, in some instances, the solute can break apart, as we will see in the following problem. In this problem, we will determine the freezing point of a brine solution made by adding 12.1 grams of sodium chloride to 2.15 kilograms of water. The freezing point depression value for water is 1.86 degrees Celsius per molal. Note that lowercase m is italicized, meaning that it is not meters, but instead molal. Also, when you're looking up freezing point depression constants, sometimes you'll find them in degrees Celsius and sometimes you'll find them in Kelvin, but the numerical value will be the same. The reason for this is both when we're looking at freezing point depression and boiling point elevation, we are looking at the change in a temperature. And because we're looking at the change in the temperature, the difference between 1 single degree Celsius and 1 single Kelvin is the same amount. So the freezing point depression is equal to the molality of the solution times the freezing point depression constant. The molality is equal to the moles of the solute, in this case the sodium chloride, divided by the mass in kilograms of the solvent, in this case water. A thing to note that for this particular solute, when you put it in water, it actually dissolves. So we won't have sodium chloride together. When we put it in water, it's going to break into sodium ions and chloride ions. What this means is that our value of our solute, the moles of our solute, is actually going to be the sum of the moles of the sodium ions and the chloride ions. Because they come from the same source, both of them come from sodium chloride, what we will find is that the concentration of all of our solute molecules will be twice that of the number of moles of sodium chloride that we put in. Again, that's because the sodium chloride breaks up into sodium ions and chloride ions. So the molality of sodium chloride is equal to our 2.1 grams of sodium chloride divided by our 2.15 kilograms of water. Now we got to convert our sodium chloride into moles. 1 mole of sodium chloride is 58.435 grams of sodium chloride. Our grams of sodium chloride cancel out, leaving us with moles of sodium chloride. Multiplying this out, you will get 0.0 Multiplying this out, you will get 0.096315 molal of sodium chloride. Now again, because sodium chloride dissolves and breaks up into sodium ions and chloride ions, our solute, the molality of our solute will actually equal the molality of our chloride ions plus the molality of our sodium ions, which will be 2 times the molality of our sodium chloride, because the sodium chloride is going to break up into 1 sodium ion and 1 chloride ion. So this would be equal to 2 times the number that we just found, which gives us 0.1926210. In terms of significant figures, our top value in our molality here has 3 sig figs, our bottom value has 3, so this value will have 3. When we double it, the end result will also have 3 sig figs. Plugging this in to our equation for freezing point depression, the change in temperature of our freezing point will be equal to our molality, 0.192621 molal, times 1.86 degrees Celsius per 1 molal, which gives 0.358275 degrees Celsius. In terms of significant figures, our end answer will have 3 significant figures. So this here would be the amount that our freezing point decreases by. If we were looking at boiling point elevation, the temperature would be going up by that amount. But because we're talking about freezing point, the temperature goes down. So our new freezing point is equal to our old freezing point minus our change in the freezing point. For water, the freezing point is 0 degrees Celsius, so that'd be 0.0 degrees Celsius minus our freezing point depression value, 0.358275 degrees Celsius, which comes out to be negative 0.358275, or equal to negative 0.385 degrees Celsius. We will look at our last colligative property, osmotic pressure, in the next video.